So we're going to start the process similar to how we did yesterday. We're going to draw our picture. We're going to draw a triangle based on the point on the unit circle that we're sitting at, with the goal of figuring out the coordinates at that point. You know I can hear you, right? Okay. So 60 degrees is a little past the halfway point in quadrant 1, so I'm up here. And how far is that point from the center of the circle? What is that radius? 1. Very good. Because that's why it's called the unit circle. A unit means 1 in math. So I'm going to do what we did last time. I'm going to draw that right triangle by... Oh, no, I'm not going to draw a right triangle. I have a thought. This angle down here is 60 degrees. So I'm going to drop a perpendicular down this way. Make a little right triangle. And if I do that, I have 60 and 90, which I'm pretty sure makes 150. If the total triangle has 180, what's left over for that angle at the top? 30. And I'm going to take this 30, 60, 90 triangle, and I'm going to flip it horizontally sideways so that I get another... Those are in... No, they're in the box because we did them last time. Another 30, 60 triangle this way. Because that is a reflection, I know two things. I know this angle at the top is also 30. I know this angle down here is also 60. I know this side is also 1. At the top of that big outer triangle, this guy here, I have two 30-degree angles sitting next to each other. 30 plus 30 is 60. This big angle here is also 60. Yay. We looked at a picture that looked kind of like this yesterday. The difference in the triangle from yesterday, which is over here, and the triangle for today, which is over here, is in this picture on the left, the long side sits along the x, and the short side sits along the y. Here, the long side is vertical, the short side is horizontal. So 30 and 60 degrees just have the role of x and y flipped. So even without doing any trig, I know that these coordinates should be the reverse of yesterday. I can kind of see that without doing any math because I know in that triangle down here, what is this distance along the x-axis? 1, because it's a radius 1 triangle. And I know that I've cut that big triangle in half vertically. Half of 1 is a half. So I know that this portion is a half, meaning the x-coordinate here is a half. And I know from yesterday with the Pythagorean theorem, if one of my sides is a half, the other side is root 3 over 2. So if I know 30, I know 60 by symmetry without having to redo my Pythagorean theorem, because all we're doing is switching the role of x and y. Good. Okay. On your test, I'm never going to ask you to reproduce those, but I thought it was good to see where those numbers are coming from so it doesn't feel like you're just randomly memorizing numbers that were pulled out of thin air. Those were calculated using something we're familiar with, Pythagorean theorem. Okay. Questions on what we talked about last time on using the unit circle to find sine and cosine, using those values to find others. No, so far we're comfortable. We're happy campers. Okay. So there are two more things I want to talk about today. First, really quick, domain and range of sine and cos, and then something called a reference angle, which is going to help us evaluate sines and coses. So first, looking at sine and cos. If you go back to your picture of the unit circle, yeah? I will draw one here really quick. That is not a circle. Try again. So unit circle, yeah. We know on this axis, we start at 0 degrees, 90 degrees, 180 degrees, 270 degrees. We end up back at 360, yeah. And I can keep rotating. That number can keep getting bigger as I complete more loops of the circle, right? But I'm allowed to trace over my pencil. I can keep looping and making more circles. So I can do 360, I can do 450, I can do 540, I can do 630. I can keep counting by 90 and keep looping and looping. For sines and cosines, my input to sine and cosine is an angle. So what are the limits on that angle I'm allowed to put into sine and cosine? If I'm allowed to keep looping over and over again. Are there limits on the numbers I'm allowed to plug into sine and cosine? Yeah, no. And I see at least one person shaking their head no. So sine and cosine can take any angle in the real plane. So the domain, the things I'm allowed to input for sine and cosine are all real numbers. Any angle on the real number line. My angle can be anything. I can take sine of 0. I can take sine of negative 1,000, sine of 1 million. It's just if it's smaller than 0, I'm going backwards. If it's bigger than 360, I've made more than one loop around the circle. Yeah. The range has to do with the output. And we know the output are the coordinates of the points on the unit circle. What is the smallest value that sine and cosine can take on? If you're not sure, go back and look at your unit circle from our unit circle notes. 1b. The smallest x coordinate, smallest y coordinate. Raise your hand once you know. Biggest is 1. What's the smallest? You can go further below 0. Negative 1, yeah. Goes between positive 1 and negative 1. Passes through 0. But the smallest is negative, the biggest is positive. If I'm looking at cosine in the x, I know my smallest is to the left at negative 1, biggest is to the right at positive. Same for the y. So my range is all of the real numbers between negative 1 and positive 1. And at some point in Math 3, you probably saw those waves. They look like waves on a graph that go up and down and up and down and up and down. We call them sinusoidal curves. They go sideways forever because they take in all real numbers, but they oscillate back and forth between negative 1 and positive 1 as their range. We're going to look more in detail at that when we start looking at all 6 functions and their graphs in our next chapter. What I want to talk about right now has to do with this fact here, which is I'm dealing with a circle. I have a limited possible number of outputs, but I'm allowed to loop forever and ever and ever. So in my unit circle, to get to this point here, I can loop from 0 to 90. I can loop from 0 all the way around once, plus a 90, which would give me 450. I could start at 0 and loop around twice before I get to 90. All of those coordinate points are the same. 0, 1. Sine and cosine are 0, 1. But the angle changes. 90 gives me 0, 1. 450 gives me 0, 1. 450 plus another circle gives me 0, 1. That very first rotation, that's between 0 and 360, so 90 degrees, is what is called our reference angle. It is the smallest possible angle between 0 and 360 with that ordered pair. Generally, we're going to focus on just the first quadrant because all of the angles here have a sine or a cos with the same value in quadrant 1. So generally, a reference angle is an acute angle, meaning it is smaller than 90, between the terminal arm and the x-axis. So 2 new vocab words. What does acute mean? We talk about angles. I say an angle is acute. I'm not trying to date it and flatter it. What does it mean when I say an angle is acute? Smaller than 90. Yeah, small. It's cute because it's small, right? Things that are small are cute. So we're talking about something between 0 and 90. And when we talk about angles, angles are produced by 2 lines. Yeah? I need 2 sides to produce an angle between those 2 lines. One of those lines is the x-axis. Because in a coordinate plane, we always start measuring from the x-axis around. The place where that angle ends is called the terminal arm. So in this picture here, if I were to draw a point on my unit circle, the angle's measured up from 0, and this line here is what we call our terminal arm. It's where the angle ends. So when we talk about angles in the coordinate plane, one side of the angle is the x-axis, the other is called the terminal arm. And which quadrant the angle sits in is determined by which quadrant the terminal arm sits in. Which quadrant does that terminal arm sit in? 1. Positive sine, positive cos. Yeah, good. Good. Okay. So, because our angle is always acute, 0 and 90, the point on the unit circle corresponding to the terminal arm will always be in the first quadrant. All quadrants, or all angles in quadrants 2, 3, and 4 have equivalent reference angles in the first quadrant. So we're going to talk about how to find a reference angle, because again, if I can have my first quadrant memorized, I can find almost any other angle that is a multiple of that first quadrant angle. So to find a reference angle, to find that smallest angle that's equivalent to the one I'm looking at, first, if the angle I'm looking at is acute and it is in the first quadrant, it is its own reference angle. So if the angle I'm looking at is 45, that's its own reference angle. It's already between 0 and 90 and in the first quadrant. So some of our angles, I don't have to do any thinking. It just is its own answer. I'm having a brain fart. Give me a second. I forgot what I wrote there. I'm sorry, Usa-chan. Don't judge me. It's been a long morning. What chapter are we on? Nope. 6. Thank you for your patience. There we go. Okay. So, if our angle is in quadrant 2 or 3, so remember quadrant 2 is here, quadrant 3 is here. So if I'm on the left half of the unit circle, then my reference angle is the absolute value of 180 minus the angle. And we take an absolute value because if I scroll up, notice that 180 sits here. If I'm in quadrant 2, my angles are less than 180. So I do 180 minus my angle, I get a positive answer. But if I'm in quadrant 3, where my numbers are bigger than 180, if I do 180 minus 200, I get a negative 20. But I want to end up in quadrant 1. I know negative 20 is a reflection of positive 20. So we want absolute values. I want positive numbers between 0 and 90. So the absolute value takes care of those numbers that are down here in quadrant 3. It's going to take them and reflect them into quadrant 1. Good. If we are in quadrant 4, so we are down here, we are looking at 360 minus our angle. And if I'm in quadrant 4, so down here, if I do 360 minus that angle, it effectively reflects me up here. So what we are doing for each of the quadrants is reflecting it back into quadrant 1. If I'm here, that minus 180 reflects it across. If I'm here, that minus 180 reflects it through the origin. If I'm here, that minus 360 reflects it up. And that makes sense because when we filled in that unit circle, we learned we could fill them in by reflecting down quadrant 1. Reference angles, we're just undoing that reflection. We're reflecting back into quadrant 1. Yeah. So you take the coordinates and you look for the equivalent point in quadrant 1 by reflection. Yeah. If the angle is bigger than 360, bigger than 2 pi, keep subtracting 360 until you get a number between 0 and 360. So you're back into a single loop of the circle, and then use those first 3 rules. So if I were at 470, my angle was 470, I would subtract 360. And what is 360 minus 470? Or 470 minus 360? I can't do math. 470 minus 360 is 110? Is that right? 120? 120? 470 minus 360? That's 110, yeah. That's 110. So 110 puts me in which quadrant? Second. Bigger than 90, smaller than 180. So the equivalent to 470 is 110. It's here. To find its reference angle, that's in quadrant 2. I go down to the quadrant 2 rule, which is 180 minus my angle. So 180 minus 110 is 70. So its reference angle would be here. So it's bigger than 360. Keep subtracting 360 until you're back on the original unit circle, and then use the rules to find the quadrant 1 reflection. Yeah. If you're able to do that, again, you can evaluate sine and cosine by just using quadrant 1. You're memorizing 3 values instead of 12. Yeah? Much faster. Okay, so you're going to be asked to do a couple of things in Delta Math. We're going to do some practice. First is you're going to be asked to find reference angles. So we're going to do 2 examples. And the first example at the bottom of page 3 says find the reference angle of 225. 225. In order to find the reference angle, I have to ask myself, first, is it bigger than 360? No. And then, which quadrant does it sit in? And Jesus says 3. Can I get a thumbs up if you agree with Jesus? I see lots of thumbs up. Good. If I go back to that unit circle we drew, I know that 225 is between 180 and 270. So it should be in quadrant 3. Good. So I'm going to make note of that. That's important. In quadrant 3. And then I'm going to go up to my reference angle directions, which are up here, and I'm going to follow the directions for if I'm in quadrant 2 or 3. And quadrant 2 or 3 says reference angle is absolute value of 180 minus my angle. So my reference angle equals absolute value of 180 degrees minus 225 degrees. So on a calculator, why did I write 2,200 and nobody stopped me? Come on, guys. Help your poor brain dead teacher out. 225. On your calculator, what is 180 minus 225? 45. And it's negative. We take the absolute value, we get positive 45. So the reference angle for 225 is 45. Good. Similar idea. We can do the same thing with radians. I just have to make that conversion in my head as to where I'm sitting. So they say find the reference angle for 5 pi over 3. 5 pi over 3. So we're going to do the same step. I need to know, is that bigger than 2 pi? The answer is no, because 2 pi would be 6 pi over 3. So we're less than 2 pi. We're in our first loop. And which quadrant am I sitting in? And I hear from Ziza 4. Can I get a thumbs up if you agree with 4? And I would give a thumbs up because that's just a little bit smaller than 2 pi. So I agree that this is in quadrant 4. It's just a little bit less than 2 pi. To find its reference angle, I look at that rules for finding reference angles for things in quadrant 4. And what do the directions tell me to do? It says 360 minus the angle, right? In this case, I want 360, but in radians. What's a full circle in radians? 2 pi instead of 360. So same idea, but I'm using 2 pi instead of 360. So 2 pi minus my angle. And I'm going to write that 2 pi as a fraction over 3. So something over 3 minus 5 pi over 3. And if I multiply the bottom by 3, I have to multiply the top by 3. 2 times 3 is 6. Yeah. The 6 divided by 3 takes me back to the 2 pi I started with. And 6 pi over 3 minus 5 pi over 3 is Pi over 3, yeah, 1 pi over 3, which is in the first quadrant, right? We know that that's equivalent to 60 degrees. That puts us in quadrant 1. Good. Yay. I'm pretty sure that's about a third of your homework for the week in Delta Math is can you find the reference angle? That's all you do. Make sure it's between 0 and 360. Check which quadrant it's in. Do the subtraction. Yeah? You don't, again, have to do a whole lot of thinking because you've got a calculator. Yeah? And you have a unit circle that has both degrees and radians on it to help you. Good. Questions on finding reference angles? Let me see somebody doing this. No? Okay. So, I had another brain fart and it's starting to hurt my head. Why can't I remember what I put on here? Okay, I know what I was thinking. All right, so to use the reference angle, we know that all angles in the unit circle have the same value for sine and cosine as their reference angle, except for a sign change. I'm going to go back up to our unit circle to look at that. So remember in our unit circle that x is cos and y is sine. Yeah? So I'm keeping track of what's happening to x and y to figure out sines. If I am sitting here in quadrant 2, is my x coordinate positive or negative? Negative. It should have the same absolute value as its buddy over in quadrant 1, but it'll be negative because it's been reflected about the axis. Good. If I'm sitting over here in quadrant 3, what happens to my x coordinate relative to quadrant 1? Negative. Same value as its buddy in quadrant 1, just with a minus sign. What about its y coordinate? Negative. So same absolute value as the guy in quadrant 1, but with a minus sign. Bless you. So if I know my reference angle, I know the absolute value of my sine and cosine. So using reference angles gives me the absolute value of my sine or cos, gives me the fraction. It doesn't give me the sign. I have to look at which quadrant I'm in to figure out the sign on my answers. Yeah. So 2 pieces. Reference angle for the value of the fraction, quadrant I'm in for the sign on that fraction. I see some nodding. Good. So we're going to do some examples. Yay. And then we will be done with our notes. Yay. Okay, so it says find the value of sine of 150 and cosine of 150 using a reference angle. I see some nodding. So first thing I need to do is, given my angle is 150, I need to find its reference angle. And I'm going to use the reference angle to then find the values of sine and cos. I know for reference angles, I have to figure out which quadrant the original angle's in. So you're going to show me on your fingers 1, 2, 3, or 4. Which quadrant does 150 degrees sit in? 1, 2, 3, or 4. And I see a whole bunch of peace signs popping up. Very good. Bigger than 90, smaller than 180. So we're in quadrant 2. And I know in quadrant 2, my sine is positive, my cos is negative. Negative x, positive y. That's going to give me my sign on my answer. I also know when I'm in quadrant 2, how do I find my reference angle? 180 minus my angle. Good. So absolute value of 180 minus 150 which is 30. So cosine of 150 degrees should be the same as cosine of 30, except that it's going to be negative because it sits in quadrant 2. I know sine of 150 should be sine of 30, because 30 is its reference angle. And it'll stay positive, because y is positive in quadrant 2. Now all I have to do is remember what the coordinates for 30 are. So 30 is the smallest angle in quadrant 1. I know these are both going to be fractions over 2. We can start with the obvious part. Who remembers the numerators for the ordered pair at 30 degrees? I heard a 3 and 1. Good. Because x starts at 3 and counts down as you go up. Y starts at 1 and counts up as you go up. Good. Done. Yay. I'm going to challenge you to do the same thing with 5 pi over 4. Take about 2 minutes in your small group. And then we will come back together. I'm going to have one or more of you walk us through how to do that. I'll even let you write on my iPad. It makes you feel fancy. Reference angles first, and then the values for sine and cosine. Reference angle first. Reference angle first. Give that 60 more seconds. I had something for you to do, and then I totally forgot to give it to you. So let me get you started on that while we wait. You're finished, right? Can I ask you to just like make happy faces down here to keep the iPad from turning off? Thank you. Okay. So I'm gonna unlock my cabinets, and ideally what I'd like is to sort it into art supplies, office supplies, cleaning products, snacks, because I have food in there, and games. If it doesn't fall in any of those categories, leave it on the desk and I will sort it out. So what I'd like to keep is these on separate shelves and them all together in the same area of a cabinet. So open. And open. I would recommend starting on the left because that's less scary. That cabinet gets a little scary. Okay. Thank you, Caesar. I appreciate the doodles. All right. So, do I have a volunteer or a table of volunteers who wants to write on the iPad and walk us through how they found their reference angles? I'll just give that right back to you then. You should write what you wrote. And if either you or somebody at your table could maybe talk while you're doing that, that would be helpful. Good. Mm-hmm. Good, because we know at pi over 4 or 45 degrees, x and y are equal, root 2 over 2. Good, very good. First question is, do we agree with the final answers? Negative root 2 over 2, negative root 2 over 2. And I see nodding. Good, because that puts us right smack in the middle of quadrant 3. The next question is, do we agree with and understand where that 4 pi over 4 came from here? And that's where I see some shaking my head. So we're going to come back to that. So this here, remember that the original rule was 180 degrees minus my angle if I am in quadrant 2 or 3. But I'm not dealing with degrees, I'm dealing with radians. So the question is, how many pi's do I need to make up 180 degrees? The answer is 1. Because remember, it's 0, half a pi, full pi, 1.5 pi's, 2 pi's. So at 180 degrees, that's a full pi. So this is, in radians, pi minus my angle. But when I subtract fractions, I need to have the same denominator. So how do I rewrite pi so it has the same denominator as 5 pi over 4? Multiply top and bottom by 4, yeah. Which is where the 4 pi over 4 came from. They took 180, converted it to radians, and then rewrote it with a common denominator. Good. So there were a couple of steps involved there. Good. Very good. Again, never going to ask you to memorize the unit circle. You have a copy of it for your homework. I have a copy of it for you for test day. Yeah? So when in doubt, you would just go find 5 pi over 4 on the unit circle and look up those numbers. Some of the reason that being able to rewrite trig functions using a reference angle is if I am asked to solve an equation or simplify an expression, and the trig functions in the expression have different angles, I can't simplify them. But more often than not, those angles are related. They have a common reference angle. And so I can take those sines and cosines and other trig functions and rewrite them all using the reference angle. And then I can start making my expressions prettier. So more often than not, when I'm finding reference angles and rewriting, I actually really only want to go up to this stage here and plug that into an expression to simplify it. Because we have the full unit circle, I don't really need a reference angle to pick off something in quadrant 3. I just go to quadrant 3 of the unit circle. I have it in front of my face. Yeah. So this is a skill we're going to come back to again and again over the next couple of units as we start learning how to simplify trig expressions and solve trig equations. Okay, on your homework for the week, some of those questions you'll just be asked to use our reference angle rules to find the reference angle. Some of the homework's going to ask you to evaluate a trig function using the unit circle, which you just pull out your unit circle, look up the answer, type it in. And then on Friday, I'm going to teach you how to find trig functions with your calculator. Some of the homework's going to ask for rounded answers from your calculator. To tell the difference, you are looking for keywords exact or rounded. If they say exact value, you are pulling that number off the unit circle. If they say rounded, you're pulling it from your calculator. Yeah? So on your homework in Delta Math, make sure you're looking for those keywords. Exact means unit circle, rounded means calculator. And that's going to be true all school year. Good. That's it. That's it for 1C. Questions? No. Okay. Paused our video here.